So I'll say a little bit about these. So review sessions are driven by your questions. I don't come prepared to talk about anything, so I'm here to answer your questions as you see fit. I would also remind you I'm in my office. If you have questions, you want to come by one-on-one, I'm also happy to meet with you there. I should be in my office tomorrow. Come by. And if you see I'm talking to somebody, just kind of stick your nose around the door and let me know you're there so that you're not. I've had people wait for me for a long time because I'm a big mouth and I talk to people a lot. So just don't be shy, okay? All right. What's your questions? Yes, sir.
Could you go through a pKa solving problem?
Okay, a pKa problem. Let's pull up a pKa type problem. Let's see. How about, when you say a pKa type problem, are you thinking about a charge problem, or are you thinking about a this one? Okay. Okay. Well, why don't I just make one up on the spot? How about that? Okay. So let's say that I've got, and let's, okay. So let's say that I've got a, I don't know, a 0.5 liters of a solution of acetic acid, and for that the pKa is 4.76. And no, you won't need to memorize pKa's. Right? And I've got a pH is equal to 5.0. Okay? And I say, what's the ratio of salt to acid for that? Okay? So there's a pure Henderson-Hasselbalch equation. You would simply say 5.0 equals 4.76 plus the log of salt over acid, right? 0.24 equals the log of salt over acid, and 10 to the 0.24 equals salt over acid. I've just solved the problem. Okay? So all that you're going to do in any problem is get it to the point where you would punch it into a calculator. Now, I strongly recommend that you organize your work and you label your work. Students always want partial credit, and we're always happy to give partial credit if we can see your logic up until the place where you made a mistake. But if you just put a bunch of numbers on a sheet, and this happens all the time, we have no idea what those numbers mean. You might, but you have to make it easy for us to understand what you're saying. So that's the number one thing I would tell you. Yeah?
The volume case doesn't matter. I think there was another example of somewhere we had like half a liter of acid and like 20 milliliters or something like that.
Okay.
Yeah.
The liters didn't matter, did it? How did I know the liters didn't matter there? So I'm not, there was nothing here I needed to do. That's not very well focused, is it? I can't see. Is it focusing? Unfocusing. Not the best. Okay, that's probably as good as it's going to get. I can't see it from where I'm at. You're getting worse or better? Worse. Say what? When? Okay. All right. Anyway, I didn't need to have any moles there, right? I had the things that I already needed. I had the pH. I had the log of S over A. I had, I'm sorry, the pH, the pKa, and that, right? Now, one of the issues, and I think the bigger question that you're asking here, one of the bigger issues is, well, how do I know to manage the information that I need, right? Part of it is knowing what does the Henderson-Hasselbalch equation require. What if I said to you, okay, that I have the following, Okay, I'll give you another example of a problem like this. Let's say I have a solution that I have of acetic acid, and I have 0.5 liters of a 0.4, let's make it 0.6 molar solution. Okay, and I have twice as much salt as acid. Can somebody loan me a pen? This pencil is just dead, or a pencil or something to write with. I promise I'll give it back. Okay, here we go. Thank you. Okay. All right. So, what do I need to work a problem like this? Okay. Well, I say, what's the pH? What would the pH of this solution be? Do you need molarity here? Do you need moles to solve this problem? I hear yes and I hear no. Right? I hear yes and I see no. Nobody said no, but I saw people saying no. What does that S over A ratio tell me? Well, if I plug this into my equation, I say that the pH is equal to, and plugging in the Henderson-Hasselbalch, pKa plus the log of S over A. I've already said S over A is 2 to 1, right? Right? So the pH of this solution will be equal to the pKa, 4.76, plus the log of 2 over 1. I've just solved the problem because I've shown what I would punch into a calculator. Right? What if I told you that I had a solution and I didn't say it was acetic acid? Okay? I didn't say it was acetic acid. And I said that the pH is equal to 3.0. And I have the solution, same concentration, at maximum buffering capacity. Does anybody know how they would approach that?
Well, at max buffering capacity, pH equals pKa, so you know the pKa is 3.
So how would you solve this problem? I'm asking you what the pKa is. 3. I'm at maximum buffering capacity, right? Okay. They're not all that way. Let me give you another one. Let's say that you have a, can't see if I'm showing up there. I have a solution that's 0.6 molar, and I have 0.5 liters of it. Okay? And it's at maximum buffering capacity. And then I add, okay, let's say it's acetic acid again. Okay. Then I add 0.05 moles of HCl. Do you know how to find the pH for that? Now, before we go and do that, I want you to think about what you need here. The very first thing I recommend that you do is think, all right? Well, yeah. Oh, I'm sorry. Being clear about the question would be important with it. All right, so the question is this. I've got this solution of acetic acid, 0.6 molar. I've got half a liter of it. And I add this number of moles of HCl to it. The question is, what is the pH? Now, this looks like it's probably a Henderson-Hasselbalch, right? So if I think about Henderson-Hasselbalch, I say, well, pH equals pKa plus the log of S over A, right? And I know that it's acetic acid, so I would have given you that it's a 4.76 pKa. And I'm looking for the pH. What would I need to solve for the pH? S over A, right? Whenever I solve an equation, I can only have one variable. So I have to know this if I want to get this. Right? Does that make sense? There's no way on earth I can solve one equation and two unknowns. There's no way to do it. I have to have one equation, one unknown. I've already said this is the unknown because I want to know what the pH is. If I want to know the pH, therefore I have to know S over A. Otherwise, I can't solve the problem. The question then is, how do I find S over A? So if you go through this logical set of steps, you can figure out what you need, and then you start asking yourself, well, how would I find it? How would I find S over A based on what we've talked about here? Anybody have an idea? What? An ice table? Is that what you're going to say? Okay. You're on the right track. So let's think about this. He says this. Remember, I've got ionization of HA going to H plus A minus. And if you remember, I said write that down first. Right? What does adding protons do to this system? Moves it that way, right? Every proton I add, what happens? I lose one of these, I make one of these, right? Everybody remembers that, right? All right. Now, how are we going to figure that out? What did we start with here? Okay. There's one important thing missing. Maximum buffering capacity. I should have told you that to start. No wonder you're confused. We're at maximum buffering capacity, and then I add this number of moles of HCl. Do you now see a way to figure that out? What does maximum buffering capacity tell you to start with? Salt and acid are equal, right? Salt equals acid. When I say the word buffer, so let's say salt equals A to start. Notice I wrote that down to remind myself that was to start, not at the end. Okay? How many moles of buffer do I have in that solution? Let's remind ourselves, first of all, that salt plus acid equals buffer. So the total amount of buffer I have is going to be equal to the sum of the salt and the acid. You got 0.6 molar, that's moles per liter, times 0.5 liters. That's going to be 0.3 moles. Okay? I'm sorry? Okay, I've got 0.5 liters times 0.6 moles per liter. I'm sorry? Okay, so let's see. 0.5 liters times 0.6 moles per liter. Can you see that okay? All right. What does that do? Well, liters cancel liters. I'm left with moles. Right? Why do I care about moles? I can add and subtract moles. I cannot add and subtract concentrations. Think about this. If I am going down the road in a car 30 miles per hour, and then I go 40 miles per hour, and I want to know how fast I went, would I say I went 70 miles per hour? No, right? But if I said I went 30 miles and then I went 40 miles, I would say I went 70 miles, right? I can add distances. I can't add speeds. I can add moles. I can't add concentrations. Concentrations are moles per liter, just like speed is miles per hour. Right? Miles I can add. Miles per hour I can't add. Moles I can add. Moles per liter I can't add. Make sense? So you see why I want to have moles? Why do I talk about adding and subtracting? Where am I going to be adding or subtracting moles? What's that? So when I add the HCl, I'm going to change moles, right? I'm going to gain some and lose some. Right? You guys aren't convincing me. I'm right. There's one thumbs up. Okay. So once I get it to moles, I can add and subtract moles. What do I have for HCl? I have moles of HCl, right? What do I have here? I have moles, and that's equal to 0.3 moles. of buffer. Notice I labeled it so I wouldn't lose track of what it was. If I just wrote moles, moles of what? Moles of buffer. What did I say buffer was? Salt plus acid. I'm sorry. HCl is a strong acid. Okay? So a strong acid is one that completely dissociates in water. That's what HCl does. Acetic acid is a weak acid. Okay? It will act as a buffering system because it doesn't completely dissociate. Okay? Anything that has a pKa is a buffer. Acetic acid has a pKa, it will be a buffer. Okay? Good question. I mean, if you don't understand this, ask questions. That's what I'm here for. I'm here to help you. Everybody understands it. Should I make a hard problem on the exam, therefore, because you understand the easy ones? Then maybe you should ask me some questions. Yes? Yeah. Finish this guy off? Okay. I will, but that's not a question. That's a request. I want a question. What do you not know? Because I'll make it as hard as I can, guys. You're telling me that you understand all this. Yeah, good.
Okay, so at this point, I don't know if this is going to the next step. So you've got 0.3 moles of buffer.
Yeah.
The amount of acid equals the amount of salt. So would you say you have 0.3 of the HA and 0.3 of the A?
No, because I said salt plus acid equals 0.3.
Oh,
Right?
okay.
So, but you're on the right track. What does that tell you then?
Then it's 0.15 for both.
0.15 for both, because I've got, that was why the maximum buffering capacity were important. I knew I had to have equal amounts of the two. So I start with 0.15 moles of each. No, I don't have H. I have 0.15 moles of this. That's the acid. 0.15 moles of this. That's the salt. Right? Don't call this the acid. Okay? All right, you guys following? Oh, that's going to be a hard exam, I'll tell you. Okay, I'm not doing this to be mean. I really want to help you. Yes? That's the concentration of the buffer. That's the concentration of the buffer to start with. HAC/AC minus is the buffer, because the buffer always has a salt and an acid. HAC is the weak acid. AC minus is the salt. In other words, it's what I've written here. There's HAC right there. That's HA. Right? There's the AC minus right there. HA is just a general way of writing any weak acid, and A minus is a way of writing any salt. Okay. Now we've established, I think, that, yeah, go ahead. Right. So when I say the word buffer, like I said, I want you to think salt plus acid. Right? And you say, what's the salt, what's the acid? Well, HAC is the acid, salt is AC minus, right? Then I told you maximum buffering capacity. When I say maximum buffering capacity, you say, got to have equal amounts of the two, right? Right, but remember that's concentration, not moles, right? Okay, but yes, it's that combined. It's always salt plus acid. That's what a buffer is. Yes?
But if you didn't know that there was that maximum buffering capacity, would you have to give the actual concentration?
If you wanted me to have you solve the problem, yes, ma'am. Okay? Yes. I always have to give you enough information so that you only have one unknown. I always have to do that. Right? Let's go through this one and finish this one. Then I'll give you another one, okay? Would that help? Okay. Let's look at this guy. So we've agreed that we have this many moles of buffer. Since salt plus acid equals mole equals buffer, I've got to have 0.15 moles of salt, 0.15 moles of acid, right? Everybody's with me? All right. So my starting material, therefore, has 0.15 moles HAC. 0.15 moles AC minus. Notice I'm tediously writing down what I told you in words because that's what I want you to do on an exam. That's how I talk about us following your logic, label your work, okay? And then I said I added 0.05 moles HCl. What does HCl do? Completely dissociates. It is a strong acid. If I put in 0.05 moles of HCl, how many moles of protons have I added? 0.05, right? That means I've got, therefore, 0.05 moles of protons. Right? Remember our equation that I had that said HAC goes to H plus AC minus? And you told me that if I add protons to that, what happens is I lose this, I make this. How many of these am I going to lose? 0.05. How many of these am I going to gain? All right, so when I'm done with that, I'm going to have 0.20 moles of HAC, 0.10 moles of AC minus, right? We're almost done. Let's go back to Henderson-Hasselbalch. pH equals the pKa, 4.76, plus the log. The final amount of salt being 0.10 divided by the final amount of acid, 0.20. There's the solution to the problem. Make sense? Okay. Yes, ma'am.
Just to go back to the beginning, in the initial question,
Mm-hmm.
you said that there was 0.6 moles of HAC.
0.6 molar. That's not moles.
Yeah, molar.
That's like saying it's
Yeah.
30 miles per hour is 30 miles. It's not, right?
I'm sorry.
That's fine. That's fine.
Okay, but then I know that like we were just discussing this, but I don't like if the HAC is equal to
Okay. Let me pull up the original. Okay, so you're confused by the fact that I wrote HAC right here, right? Okay, so that's a buffer. So that's, I more accurately could have written that saying HAC/AC minus. Does that help? Okay. So whenever I use the word buffer, I'm talking about the salt and the acid. But your confusion, and that's a good point. This is one of the problems with making a problem up in front of a class. Is if I sit down and write one for an exam, I think about all these components, but as I'm making it up in front of the class, I don't think about the confusion that you might have with it. If I ask you a question on Friday and you don't understand what I'm asking you, raise your hand. I'll be happy to answer your question. Okay? I can't tell you the answer, obviously. But if I realize I'm not being clear, I will tell you. And if it's not clear, then I'll announce it to the class. Say, hey, class, listen, here's a question. I didn't think about this. All right? I want to make it clear what I'm asking. But you do understand that, okay?
Yeah.
Okay. Yeah.
So, if we got this question as a short answer, would you want the answer as what you showed it to us with the equation, or do you want to actually solve it out and give you the pH? So, no, for multiple choice, you could figure out what you were asking.
So all I want to see is you getting it to the point you would punch it into a calculator. That last step that I showed you is fine. Because if you punch it into a calculator and you get it wrong, you're going to get the problem wrong, even though you had that step right. Right? So get it to the point you would punch it in a calculator, and you're done. If you got it right, right? But if you get it wrong, you see what I'm saying? One of our policies is if you write something down on a sheet and you write it wrong, and you've got something else on there that's right, you'll still lose points. Okay? And the reason for that is we don't want people guessing. Some people will try to answer a question by writing everything under the sun that they can about it, right? And then, we just can't have that. We have to have you addressing the question that's there. So if you write extra and it's right, that's fine. But if you write extra and it's wrong, you're going to lose points. points. So that's why I say just get it to the point you punch in a calculator. Right? We're not rigid about this, okay? I don't want to mean so. We're going to pound you on the head. You're welcome to bring a calculator, all right? But my strong advice to you is not to use it. You're not going to need it, all right? The problem is that you guys have been conditioned to think of math as numbers, right? And math really isn't those numbers. Math is how you use the math. That's what I call the practical side of math, okay? The practical side of math. You're welcome to bring it, all right? But my strong advice is don't use it. You're not going to need it. Yes? Sure. You may try to make one up again on the spot here. I'll see what I can do. Let me think for a second. Here's one. Let's say I've got an unknown buffer. And I have, let's go with our standard here, 0.6 molar. And I've got 0.5 liters. Okay? We've already been there. We already know how many moles there are of buffer, right? Let's say I have twice as many moles of salt as I do acid. How much, I said salt is acid, how much HCl or NaOH would I have to have twice as much acid as salt? So you're going to tell me which one you're going to need and how much. Okay, so I'll write it down. So I've got salt over acid equals twice as much, 2 to 1. How much, my writing is terrible, much HCl or NaOH to get salt over acid equals 1 over 2. Okay? Everybody see what we're trying to do? What do we have to do to go from 2 to 1 salt to acid to get 1 to 2 salt over acid? What do we got to convert into what? Okay, so he says I got to convert salt into acid. And if I'm doing that, I need to use HCl to make that conversion. Does everybody agree with that? Good. Good. Okay. So I'm going to have to add HCl. So there's the first part of the problem. Okay. Now the question is, how much do I have to add? Yes? Well, okay. We'll see. We'll see. Let's think. What is our starting amount that we've got of salt and acid? Start salt equals what? Okay, so I hear 0.15 and I hear no. You guys can duke it out. You're all okay. What do you say here? Okay, so I picked numbers because, of course, the last time we did it, we had that acid equals 0.1, right? And you decide I'm going to add acid. Question? The ratio is 2 to 1. So, all right, so that's fine. Okay, so there's 2 things here. Salt plus acid equals 0.3. Salt over acid equals 2, right? No, but I'm going to show you. I'm going to show you. You guys are already getting to this because you saw the number last time. This is why I don't like you looking at old exams, because you see the pattern. that you just all dove into? You did two things here. One was the first thing you decided was 0.15 because the last one it was 0.15, right? And the second thing was, oh, I know what it is because I knew what it was last time. But what if I didn't give you something just like it was last time? It was a slightly different number. So I want to show you how to approach it logically, okay? I'm not trying to pick on you here, but I want to see how you approach this logically. All right, salt plus acid equals 0.3, salt over acid equals 2. That must mean that salt equals 2 times acid, right? So now I've got two equations, two unknowns. What if I take the first equation and I say salt equals 2 acid, therefore I've got 2 acid plus acid equals 0.3, right? Everybody with me? Therefore, 3 acid equals 0.3. Acid equals 0.3 over 3. Acid equals 0.1. And since salt is twice acid, salt's going to be 0.2. You follow that? That's how you go for it. Don't rely on what I remembered from how I saw it on an old exam. That's why old exams get you in trouble. Everybody's smiling now. They know what I'm talking about. Okay? Good, good. You got a good head on your shoulders. Okay? Don't turn it off. Use that good head. You guys know how to do 2 equations, 2 unknowns. Yeah. Okay, okay. Let me finish this then. All right. So we've decided we started with 0.2 salt, 0.1 acid, and we want to get to what? We're going to flip that, right? So we're going to flip it. We're going to have 0.2 acid, 0.1 salt. How do we get from 0.1 acid to 0.2 acid? I'm sorry? What's the difference between those two? So if I add 0.1 moles of HCl, how much salt am I going to convert to acid? I'm going to convert 0.2 moles into an additional 0.1 moles of acid. I'm going to lose 0.1 moles of salt. I'm going to gain 0.1 moles of acid, right? Am I right? Okay. Did you notice how thinking about that last problem made you think that it was 0.05? Ah. Use your heads here, guys. Work through the problems. Okay, I see anxiety now, right? I'm not going to try to trick you. I can absolutely assure I'm not going to try to trick you. I will always try to test what you know. All right? Questions about this? Mm-hmm.
Where is that coming from again?
So I said salt equals 2 times acid, so 2A is the same as S, right?
Mm-hmm.
So I've just replaced S with 2A.
Oh, okay.
Right?
Got it.
Okay? Questions? Yeah. Okay. Are there questions on this? Everybody understand this? Yeah. I said how much HCl. We decided we're going to add HCl, right? And you told me that adding 0.1 moles of HCl was going to convert 0.2 moles of salt into, if I add okay, let me write it out. So I have 0.2 moles of salt. I have 0.1 moles of acid, right? I add HCl because I need to convert salt into acid, right? Everybody's with me there? The final, this is start. The final is I have 0.1 moles of salt, and I have 0.2 moles of acid, right? Because I went from a 2-to-1 ratio to a 1-to-2 ratio. Right? Everybody with me? So how do I go from 0.2 moles of salt to 0.1 moles of salt? I've got to lose 0.1 moles of salt, right? If I lose 0.1 moles of salt, I gain 0.1 moles of acid. What's going to convert 0.2 moles of salt to 0.1 mole of additional 0.1 mole of acid? That's going to be 0.1 moles of HCl. Okay? Does that answer your question? You okay? Okay. There were some people you had another question, and you had another question about something else. I'll start with you since you asked it first. What was your other question?
We could go back to the structure of amino acids and maybe talk about
Okay.
which acids get ionized.
Okay.
Talk about how the pKa.
Sure. Let me ask that first. Are there any other quick questions about buffers? If you're having trouble understanding buffers, come see me. I'll be in my office tomorrow. I'll also be in my office on Friday. Okay? I'm happy to go through those with you. I think I should go on and talk about amino acids and so forth. Okay. And was that your question also, or did you have a different question in the back?
My question kind of has to do with the philosophy.
Okay. So you don't have a buffer question? Okay. All right. So let's talk about amino acids in charge, right? So you've seen I've got practice problems out there that say, okay, here's an amino acid that I made up. Let's call it Ahernium. If I can spell Ahernium. Ahernium, right? And Ahernium looks like this. COOH and COOH and COOH and COOH and NH3+. There's Ahernium. I just made it up. Okay? Somebody said, I don't know how to solve the problem because I don't know which ones are the R groups. I'm sorry? I'm just making this one up. The one I got asked about online is a similar thing. I said, I don't know which one's the R groups. I said, doesn't matter. All that matters is what ionizes. I can call this the alpha carboxyl if I want. I could call this one the alpha carboxyl if I want. For this purpose, it doesn't matter. As long as I know the pKa's of each one. Let's say the pKa of this guy is 2.0. Let's say the pKa of this guy is 4.0. This guy is 6.0. This guy is 8.0. And this guy is 12.0. If I know the pKa's, I automatically know something about how they behave in solution. Doesn't matter what I call them, whether I call it alpha carboxyl, I call it alpha amine, it doesn't matter. Right? So let's say I've got this guy in a solution with a pH of 10. And I said to you, what's the charge on this guy? Okay. You would first of all need to know the rule that I gave you that I said I wasn't going to give you on an exam, which is you need to know that the pH is one or more units above the pKa. Proton is off. If the pH is one or more units below the pKa, the proton is on. Right? So now all we have to do is apply that rule to this problem. We look at each group and we say, well, is the pH above or below the pKa, and is the proton on or off? Well, if I look at the first guy right here, the pH is 10, the pKa is 2, pH is higher, so the proton is off. If I look at this guy, there's a pKa of 4, a pH of 10, that proton's off. I look at this guy, same thing, 10 is greater than 6, that proton is off. I look at this guy, say 10 is greater than 8 by 1 or more units, that proton is off. And I get over here to the amine, and I say 10 is 1 or more units below the pKa. That means that the proton is on. That's the structure of that molecule. And the charge in that molecule is 1, 2, 3, 4 minuses and 1 plus, an overall charge of -3. Make sense? Yeah. Okay. What if it were 9.5? Let's do the same thing. If the pKa were 9.5 or the pH? Okay. If the pKa were 9.5, for this guy you're saying? Or anything, right? Yeah. Right. So if it's not 1 or more units, let's say that I had a pKa value here of 9.5 and I said the pH was 10. I would want you to look me in the face and say, I can't predict that one. And you would be right. Because it's not 1 or more units above or below. I just made it easy for you, I hope. Okay? Do you follow? Yeah. So the zero charge is NH2. So when it's NH2, it's 0. When the proton's on, it's NH3 and it's plus. Yeah. There would be a charge of 0. That's right. Is there a question over here? Yeah. That was your question? Okay. Okay. So with amine groups, you have an NH2, which is a charge of 0, or you have an NH3, which has a charge of +1. With a carboxyl, you have a COO minus without the proton, COOH with no charge with the proton. Okay. That's something you should review from your organic chemistry. Okay? Yeah. That's right. Right. So the ones like aspartic acid, glutamic acid, are both, when they have the word acid in them, have carboxyl groups with COOHs, which can be either COOH or COO minus, depending on the pH and the pKa. And the three basic ones, lysine, arginine, histidine. They can have NH3 plus or NH2 with its charge of 0. Yes, sir?
I do have a question about it.
Yeah.
What pH would be required, and this is super conceptual, for that NH3 to be NH3?
Okay, that's a very good question. What is the minimum pH that would be necessary for that guy to have a charge of -4 overall? Right? That's what you're saying, right? What's the minimum pH that you would need to have this guy have a charge of -4? Okay, so let's think about the rules. What do the rules say? What takes a proton off? pH 1 or more units above, right? Below means the proton's on, right? So 1 or more units above the pKa, so that would mean you would need to have a pH of at least 13, right? Yes, ma'am. This guy has a charge of -3, 4 minuses and 1 plus. So to have a charge of -4, I'd have to have this last proton come off, leave it a charge of 0, right? You understand? Very good. Good. I'm happy to see that. Yes. Yes, ma'am. If the pH, state the rule the way I said it now. Be careful, okay? Because you'll get yourself in trouble if you don't. If the pH is 1 or more units below the pKa, the proton will be on. If the pH is 1 or more units above the pKa, the proton will be off. This is where students screw it up on an exam. They know it's 1 pH unit, but they can't remember which way because they haven't practiced in terms of getting that thing right. Make sure you say it right. Nothing, as I said, would make me happier than if everybody got that right, okay? But just don't look at greater or less than. Look at 1 or more units above. pH is, and by then memorize this. If it's 1 or more units above, then the proton's on. What's above? The pKa is above or the pH is above. So be careful. If the pH is 1 or more units above the pKa, the proton will be off. If the pH is 1 or more units below the pKa, the proton will be on. Do you have a question? Yeah. Sure. Let me do one like that. How's that? Is that your question, or do you have a different question?
No, I was going to continue on with this one a little bit.
Okay, go ahead.
Okay, so let's say it was 13, and now we have NH2.
Okay.
Okay. If it went all the way to 14, you then go to NH.
No. So there's only two possibilities for all these. One proton on or one proton off. So carboxyl, 1 proton off is COO minus, 1 proton on is 0. Amines, 1 proton on, NH3 plus, 1 proton off, NH2. And that's as far as it goes. Okay? Good. Okay, let me answer your question back here, which is another way of looking at the same thing. Okay? The other way of looking at the same thing allows me to find out 2 pieces of knowledge from you at once. The 2 pieces of knowledge are, do you know your amino acid structures? And do you know the relationship between pH and pKa with respect to protons? I'll give you one right here. I'll give you a hard one, okay? I'll give you a hard one right here. Let's say I've got the following polypeptide chain. Let's say I've got arginine, linked to leucine, linked to tyrosine, linked to aspartic acid, linked to glutamic acid. I could give you that on an exam. And I said, let's imagine the following rules. The following rules are as follows. Alpha carboxyl, pKa's. Alpha carboxyl is 2.2. Alpha amine is 9.5. Okay. R group carboxyl is equal to 4.4, and R group amine is, let's say, 12. And I tell you, I've got this guy in a solution that has a pH of, I don't know, let's say 6. What's the charge on this molecule? Is that what you're after? Okay. Now, there's an easy way to approach doing this. Whenever you've got a polypeptide, there's some very good simplifying things. I'm standing in the way, aren't I? Some very good simplifying things. The simplifying things are, I don't have to worry about the charges between the individual peptide bonds. Peptide bond charges disappear. I only have to worry about the alpha amine, which is the very first one, and the alpha carboxyl, which is the very last one. All the alpha carboxyls and alpha amines in the peptide bonds, I don't have to worry about those. So what I like to do when I work a problem like this is I will mark it. So I say, okay, let's don't forget we've got an alpha amine out here, and we've got an alpha carboxyl over here. We'll decide if the protons are on or off later, right? The only other thing I have to consider are which R groups can ionize. That's why I told you that you're responsible for knowing which R groups ionize and how they ionize. So which ones will ionize here? All right. Well, the answer is, here's an R group that will ionize, and it's amine that will ionize like that. And here's another one that will ionize, R group, with a carboxyl. And here's another one that is an R group with a carboxyl. Now what I've done is I've identified all of the things that can ionize. Everything that can ionize I know on this molecule right now. Let's apply our rules. The pH is 6. Here are the pKa values. What's the charge on this guy? Well, let's go for each one. Here's an alpha amine. Right? Alpha amine has a pKa of 9.5. The pH is 6. Proton on or off? Proton, the pH is one or more units below the pKa. The proton is on. Okay? That means I've got an NH3+. plus. Here's an R group amine. pKa value of 12. pH is 6. Proton on or off? On again, right? pH is one or more units below. Got a plus, right? Here's an R group carboxyl. R group carboxyl has a pKa value of 4.4. pH is 6. Proton is? pH is more than 1 unit above the pKa. Proton is off. That is a minus. Here's another R group carboxyl. Same thing, right? Here's an alpha carboxyl. pKa of 2.2. pH is 6. Proton is off. There's my molecule. Now I just simply add up my charges. 1, 2, 3 minuses, 2 pluses, overall charge of -1. Make sense? If you do this systematically, you'll get it. Okay? But remember that rule. That's the most important thing. Don't just remember the one or more units. Okay? Don't remember above or below, because it's got to be the specific thing above or below, the pH or the pKa. Dominique? Do you need to know how to calculate the PI? I showed you how to calculate the PI on that graph. So I think that's probably a reasonable thing for you to understand how to do. Yes. Yeah. Okay? If you need to leave, feel free to leave. Yeah. So take care. Don't forget your cup. Yes.
So getting back to this, so when you look at that, only look for either your acidic or basic amino acid groups.
That's right. They're the only ones that ionize. And on the R groups, yeah.
Cysteine.
I told you cysteine. I will tell you right now, I'm not going to ask you cysteine.
Okay.
How about that? We'll keep it simple.
In general, though, cysteine
Cysteine can ionize.
and it's the only one of the polars.
Well, it turns out the tyrosine actually can as well. I didn't tell you that.
Okay.
So, but we'll just keep it simple. We're going to have the carboxyls and the amines as the only ones, okay? Unless you want to make it harder. No, nobody ever wants me to make it harder. Yeah, back in the back. Sure. I can go over them. I'm not sure what to tell you, but I will tell you something about them. Hydrophobic bonds. Now, what you're talking about are two types of bonds that help to stabilize tertiary, my shirt keeps coming untucked, tertiary structure and quaternary structure, right? Remember the forces? What were the forces that held together primary structure? Peptide bonds. What are the forces that hold together secondary structure? Just hydrogen bonds. The peptide bonds are only involved in the primary structure. Okay, yeah?
What about the disulfide bonds in secondary structures?
So there are some disulfide bonds that occasionally are found in secondary structure. They're the exception rather than the rule. So the predominant forces that stabilize secondary structure are actually hydrogen bonds. Okay? But yes, there are a few that do that. Okay. What are the forces that hold together tertiary structure? Disulfide? Well, those are covalent bonds. Ionic bonds? Hydrophobic bonds? Hydrogen bonds? Metallic. Okay? So he's asking about metallic, and those are the same forces that hold together quaternary structure. Exact same forces. Right? Now he's asking about metallic bonds and hydrophobic bonds. So what's a hydrophobic bond? What's hydrophobic itself mean? Doesn't like water. Means it's not polar. It's not going to hydrogen bond with water. So when we see carbon-hydrogen bonds, they're covalent bonds, and their electronegativities are not very different. So there's very equal sharing of electrons there, so we don't see polarity. Therefore, carbon-hydrogen bonds will not interact with water. That's why they're hydrophobic. And so we look to amino acids that have carbon-hydrogen bonds, or mostly carbon-hydrogen bonds, in their side chain. We will identify those that are hydrophobic. Leucine, alanine, valine, okay? Isoleucine, okay? These are methionine. They're all hydrophobic side chains. They don't like to interact with water. And just like oil doesn't like to interact with water, oil will associate with itself. That's why it separates from water. Amino acids with hydrophobic side chains will try to associate with each other if they can do that and avoid water. So in the folding of a protein, proteins will fold so that the hydrophobic amino acids interact with each other, and that forms what's called a hydrophobic bond. Okay? That interaction between those hydrophobic side chains avoiding water, okay, that's making a hydrophobic bond. The hydrophobic bond wants to stay together. It doesn't want water in there. So it's actually a force of stabilization. That's why we say it's a hydrophobic bond, because there's something holding that together. Now metallic, question, I'm sorry. Yes. Yes. Okay. The metallic bonds I didn't really say too much about. They largely form between metals and carbons, or metals and nitrogens in amino acids. Okay, we don't need to worry about the exact structure. The metallic bonds that you've seen so far included the bonding of the iron in heme. I showed you how that histidine bonded to the iron, and that was important because when the iron moved, the histidine moved, and and hemoglobin changed its structure, right? That was a metallic bond that was holding that. So metallic bonds can also give some stability to tertiary structure. I said they're not a major contributor, but they do provide some stability for a tertiary structure. Everybody getting hungry? Other questions? I'm not trying to rush you. Other questions? Yeah? How does vitamin C help stabilize collagen? Okay. So let's think about collagen. Collagen is what kind of a protein first? It's a fibrous protein. And it's a fibrous protein. It has 3 fibers that are intertwined, kind of like a braid that I give the analogy to, right? It's like a braid. And if I think of that braid, I said that braids are more likely to stay braided if we link the individual chains of a braid together, like holding it together with a rubber band. If we were to make bonds between individual braids, then that would be another way of doing it. Instead of putting a rubber band at the end, it'd be kind of like putting rubber bands in the middle, right? Those bonds that hold things together in the middle arise from hydroxylation of proline. So adding there, we're making hydroxyproline. That was an unusual amino acid we see in the collagen. That hydroxylation is necessary for making those bonds. Okay? It's the hydroxylation, the putting on the hydroxyl groups, that requires vitamin C. The enzyme that does that needs vitamin C to do that. I didn't give you the name of the enzyme. Yeah. But it's an enzyme that does that hydroxylation. What's the disease you get if you don't have enough vitamin C? The class woke up. All right. I'm happy to hear that. You guys are a very quiet group. I try to pull things out of you sometimes. And you don't have to talk. I understand that. But I do like it when the class communicates. That made me feel good. Yes? A question that would involve protein separation. I'll make one up here. I can't promise you're going to see it on the exam, but I'll make you one up here. Okay, how about that? Would that help? Let's imagine I said, tell me about a method of separating things that I described in class in which the largest molecules move first, move the fastest. What would you say? What? Gel filtration, one answer. Everybody agree with that?
If you were to ask something like that, if you couldn't come up with a specific name, but you could describe how it works and how, like, the later ones that you first, would that be right?
Well, generally, if I'm asking for a name, I will want a name. But if you don't have a name, then I would certainly tell me as much as you know. Yeah. Okay. But I do place a fair amount of emphasis on names. So that's why I say, quiz yourself or study with somebody and quiz each other about things like that, because walking the walk's important. So the answer is gel filtration, yeah. Okay. Because gel filtration, the big guys couldn't get into the little tunnels, you remember? And consequently went around the beads instead of going through the beads, and they traveled a shorter distance. And that's the answer to that one. All right. Tell me about a technique that, one more question, I'm going to give her one more question based on her thing. A technique that separates molecules on the basis of their polarity. What's that? That's actually based on charge, which is a type of polarity, but I'm looking for something more specific. HPLC. Okay. We had the packing material, had those long nonpolar side chains. The polar molecules came out first. The nonpolar molecules came out last. Okay. And you have a question over here, sir? Somebody did over here. Oh, you had. Okay, I don't know who had the question. Yep. Yep. Yes, gel filtration is different from electrophoresis. So gel filtration relates to the beads with the tunnels in them. Okay. And so it's kind of a passive process if you think about it. The solution goes through, the molecules, just kind of pass through. And the question is, which goes the fastest? Well, the ones that go the fastest are those that don't travel through all the tunnels, right? Gel electrophoresis is not a passive process. It's using electricity, in an active way to move molecules through that gel, right? Okay. So there's an electrical charge. That's why you have to have, in the case of DNA and protein, you have to have that negative charge because it's relying on the electricity to actually move that, right? Good. Did you have a question? Or? Oh, okay. I thought somebody over there did. Yes?
Would you, so, I'm sorry if I pronounced it wrong, before we went over it, for the graphs that measure like the Vmax versus
Uh-huh.
the substrate concentration,
V versus S.
are you going to give us math type problems with those, or are you going to give us more
Okay.
like concepts?
Okay. So the question is, if, when we look at enzyme kinetics and we're thinking about V versus S and so forth, am I going to give you math type problems with those or concept type things? You are not going to do math problems on that. Okay? So that's why I say I'm not going to give you numbers and say plot this because that would take too long to do. But I might say sketch out, here's a good example. Sketch out a V versus S for a uninhibited reaction compared to a non-competitive inhibited reaction. Do you know how you would do that? All right. Let's go through the thinking process. Thinking process. What's the difference between a non-competitive inhibition and a uninhibited reaction? What changes? We said something changed and something didn't change. Do you remember that? Vmax changes, right? So now we start thinking about how would I sketch something like that out? Well, I start by taking a look at V versus S, right? I say, well, if this is my uninhibited reaction and there's Vmax, what's the non-competitively inhibited one going to look like? It's going to flatten off at a different point. Non-competitive, right? Yes? With non-competitive, Vmax decreases, yes. Okay? And that's what I've shown here. Notice it didn't flatten out at the same point. It flattened out at a lower place. If I were to ask the same question for competitive, what would it look like? It would look like this. And would eventually flatten out at the same place as the uninhibited, right? Make sense? This is where I like to see smiles. Or if I had that scurvy reaction here, that would be good, right? Just say scurvy and I'll be happy. Yes?
This one here, is the Km the same for both of these curves?
Okay, so what changes with competitive? Nope. Vmax stays the same for competitive because, right?
Yes.
Okay, so what changes for competitive? Let's think about it. Here is Vmax over 2. Do we all agree with that? Right? Roughly half of what this value is here. Everybody with me? What is the Km for the uninhibited reaction? Well, I go over here and I say, there's the Km for the uninhibited, I'm going to put a U there, reaction. What's the Km for the competitively inhibited reaction? Well, it's way over here. Km competitive inhibited. The Km is increased.
More specifically for the non-competitive inhibitor, that's the same, correct?
So for the non-competitive inhibitor, the Km does not change. That's correct. And you might say, well, look, it's way over here, right? Except for the Vmax has changed too. So I've got to do a new Vmax over 2. And when I do that, I'm not going to do it on this graph, you'll see that the two Kms align. Everybody's frowning at that. All right, I knew I shouldn't have put this on here, but I'll do it. All right, here, all right, let's look at this. Here's the non-competitive. So this is the Vmax, or let's say right there's the Vmax for the non-competitive, right? Where's the Vmax over 2 for the non-competitive? It's about right there, let's say. So what's the Km for it? Well, I go over here, okay, and I say there I am with the non-competitive. Look, they line up. The Kms are the same. Now, I said the non-competitive, you're just going to have to trust me that the Km stays the same. if you want to come talk to me, nobody has come talk to me about it yet, so I kind of mean that I don't give a shit about that, right? Come talk to me. I'll be happy to talk to you about it. But if you just know that the non-competitive, the Km does not change, you'll be okay. Okay?
So the Vmax over 2 is roughly half of where each line.
It would be half of where the Vmax is. So if the Vmax is here, then halfway up there would be Vmax over 2, right? You guys ready for happy hour? That was a yes, or that was another question?
Sorry. Something about that overall charge is kind of bugging me.
Okay.
And the alpha amine,
Okay.
terminal amine, I guess, was arginine.
Say it again.
Was arginine.
So the
And it
alpha
was
amine,
connected here,
that's the alpha amine.
and this is its
That's the R group amine. Uh-huh.
And I see an NH2.
Mm-hmm.
And on your example, you have the PK, the pKa of
Mhm.
this NH2 is 12.
Mhm.
It was written up there as NH3 with
Mhm.
a plus,
Okay. So this is showing with a 0.
right?
So if I put another proton on there, I'll have an NH3 plus. Right?
What was that example again? You had the pKa was
So in other words, if I have an amine with an NH2 on it, it's a 0.
right.
Okay? And that's a 0 right there. If I put a proton on there, I'll have an NH3 plus.
Okay.
Right?
So you were taking them off of the other ones and putting it on, putting a protein.
So on the arginine, I had two. The arginine was on the end, so I had an alpha amine and I had an R group amine. There's the alpha amine, because that was the only one that had the free alpha amine.
Right.
There's the R group amine. So they both had protons on. I think that's what's confusing you.
Does the terminal amine always have is it always NH3?
If it's got a proton on. If it's NH2, if it's got a proton off. So whether it's NH3 or NH2 depends on the pH and the pKa, right? Here's your pen before I forget. Yeah, thank you.